Well, hello, thank you for joining. My name is Steve Quarles. I am a retired cooperative extension advisor with the University of California and a retired chief scientist for wildfire and durability for the Insurance Institute for Business and Home Safety. Today, I'm going to be talking to you about wildfire in the built environment. I'm going to focus on mitigation strategies, and I appreciate the opportunity given to me by the Fire Safety Consortium to present here today. So today, during this particular lecture, I'm going to be talking about or summarizing the wildfire exposures to buildings and discuss some of the vulnerabilities to buildings and their associated mitigation strategies. The picture we're looking at here, I took in the late 2000s. It's an interesting picture to me because this particular fire started within a mile of the 1991 tunnel fire, which was the Oakland Berkeley Hills fire in California. And this happened some years later, but I think that the importance of this picture is that the fire is well under control. You see helicopter dumping water and a lot of firefighters on the hill and other apparatus clearly there because of firefighters with a fire hose. The thing that was different between this particular day and the day that the tunnel fire became a big fire was weather. So we did not have extreme weather on this particular day when I took the picture that was present on the day of the tunnel fire. So weather is an important part, and I think this is just sort of shows that with not so bad weather, typically wildfires can be put out pretty quickly. So there are three basic exposures. I'm sure you're all aware. Embers or firebrands. I don't distinguish between the two. So I typically use the word ember, and I'll use that today. But when I say ember, I mean the same thing as a firebrand. Flame contact exposure and radiant heat. These are the things that homes have to resist if they're subjected to exposed or threatened by a wildfire. This is just a schematic of the same thing at the upper left, showing embers. So, leaping over whatever happens to be on the property typically, and then igniting something near the home or building or on the home or building, or entering into the home or building through an open window or through an vent, for example. The upper right, radiant heat, either from the fire itself or from a spot fire. In this case, we see that the shed on the property has been ignited, and then it's a radiant heat exposure from that shed to the window. And I think based on this figure, you can assume that the glass was broken and curtains, for example, ignited. And then the third, direct flame contact, the lower right, fire is able to burn directly to the building and potentially ignite the building in that way. Well, we know that embers are really important. We can see that in these two pictures here. The left-hand picture is from the Angora fire in South Lake Tahoe, 2007, South Lake Tahoe, California, 2007. A destroyed home with a lot of green vegetation around it. It's sort of indicative that embers ignited the home either by landing close to it, on it, or in it. And then the right-hand picture is from the Tubbs fire, 2017 Tubbs fire in Santa Rosa, California. This is a big box store. The brick wall on the right is the big box store on the outside. And then on the inside is the upper right-hand picture, pretty much destroyed. This is in the middle of a big parking lot, so clearly the fire didn't burn all the way to it. It was, again, indicative of an ember exposure. So I think embers are important because of what they can do directly and what they can do indirectly, and we have examples of these on this slide. The left-hand picture is a fence exposed to an ember exposure, exposed to embers in the test facility at the Insurance Institute for Business and Home Safety Research Center in Richburg, South Carolina, where I worked for a number of years. And here we're seeing embers that ignite the fence directly without the help of anything else but the material and the fence. And you'll notice that there's a horizontal ledge and vertical planks, the embers, accumulated and in this ledge to vertical plank intersection and ignited, and a post, and ignited the post directly. So no vegetation, just the materials in this case, fence. And the right-hand picture is from the IBHS Research Center in a demonstration we did way back in 2011. But we see a number of examples of what I would call an indirect ember ignition scenario. So embers ignite something in the gutter, on the ground by the home, in these two situations. So in this case, it's pine needles in the gutters and bark mulch on the ground right by the home. The upshot is that indirect ember ignition scenarios ultimately result in either radiant heat or a flame contact exposure to the building. So debris in gutter ignites our flame impingement on the edge of the roof, ember ignited bark mulch, flame impingement exposure to the side of the roof, to the siding on the building. The left-hand gutter is a vinyl plastic gutter, so it detaches and falls to the ground. It's an edge of the roof challenge until it falls to the ground, and then it's what's on the ground issue in terms of the vulnerability that it, or the threat that it might pose to the building. The right-hand gutter in the right-hand picture is a metal gutter, so pretty much the gutter stays put and it stays an edge of roof issue until the debris in the gutter burns out, assuming it doesn't ignite components at the edge of the roof. Just want to show you a quick video. This is a nighttime test at IBHS. It just, because it's nighttime, you can readily see the embers. This is typical ember exposure. In this particular series of experiments, we're evaluating the vulnerability of vents to ember entry. And at this particular test, it's evaluating the performance of a gable end vent. But a couple of things to notice is how the embers sort of roll back after they hit the building, and they accumulate in front of the building, not directly at the roof, the wall necessarily, but away from the building. And we'll talk about this a little bit more. And then how they circulate around the building. Anyway, I think we're seeing this enough. Well, okay, here we go. And then this is a demonstration we did again in about 2011, and it does, I think, point to some of these indirect ember ignition scenarios. This was our first generation of ember generators, largely based on the NIST generators several years ago. The IBHS generators have sort of been evolved over time, and now they're no longer a batch process load, but in this series of experiments, they were a batch process load. Here, so you see embers accumulating against the window screen, and you're going to start seeing ember ignition of debris in gutter, bark mulch on the ground. That will ignite vegetation plants near the building, and then impinge on the siding, the edge of the roof itself. So you noticed already that the vinyl gutter has detached and fallen to the ground. We have fire burning into the reentrant corner, the interior corner there. You'll notice that that fire is going to get big pretty quickly because of the re-radiating effect from side to side on this building. Debris in the valley there igniting. This is a looping thing, so that gutter that you see has already detached before. Again, the interior or re-entrant corner, big fire. This is what caused us to extinguish the fire. We wanted to protect the building ultimately at the end of the day. So I think we'll stop it there. And so those were sort of ember ignition scenarios. There clearly are times when radiant heat can be a problem, and these are when buildings ignite and you have a neighbor that's pretty close by. And we saw that in the diagram of the shed to building exposure, or radiant heat exposure. This is an Eastern Tennessee fire in the United States where building to building or home to home, ignition scenarios occurred pretty readily after initial ignitions, and these two pictures are the same building, just a minute apart or two, well, actually 5 or 10 minutes apart. But the left-hand picture, you can see that little flame, and the peak or the ridge of the roof. There was a window in that area, which likely was broken by the radiant heat from the burning building to the right. And then that fire spread throughout these homes that were built on the side of the hill. These are 3 to 5 story homes, and a lot of combustible materials inside. So in this case, clearly things that could resist radiant heat exposures would have been a good feature to have. Again, another example of where home to home was likely a big part of the wildfire, so it sort of became an urban fire, was the 2017 Tubbs fire in Santa Rosa, California. This was the Coffee Park area that I'm sure many of you have heard of. Many homes in this area were, in this development or neighborhood, were burned. The red houses on the right-hand figure are all the houses that were destroyed. So again, an example of where materials would become more important. How far away can buildings be? It's sort of it's important and now in the United States, at least, a heavily researched topic. There is a series of experiments currently underway, largely funded by the California Department of Forestry and Fire Protection. The money is funding experiments at NIST and IBHS, and they're nominally called the structure separation experiments. Here's a couple of pictures of that. It's a 3 or 4 year project, and the first year is completed, and reports are starting to come out on the results. I think the initial year was sheds to a facade or shed to a building kind of exposures. In subsequent years, the building, the source building would become larger, and the target building stays about the same. There's additional research on structure separation kind of experiments being conducted by the Fire Safety Research Institute. So I think if you Google either one of these, you'll learn more about the current state of the research at these various institutions. This is something that I've observed over time, and Barrow observed it a long time ago in 1945 when he wrote his report after the 1944 Emeritus fire in Australia. I think it really points to how we need to think about ember ignition scenarios in particularly the direct ember ignition scenarios. And that is this resistance to wildfire is determined more by the details than the material itself. And an example of that is on the right-hand picture, where we have a non-combustible tile roof covering with a bird's nest underneath the roof covering on the roof deck. So ignition of that bird's nest by embers will result in flame contact exposure to the roof deck. And this, in essence, bypasses the protection offered by this non-combustible roof covering. So part of this mitigation strategy would be to plug those holes to make sure that A, birds and other debris don't get under there, and B, during a wildland fire, embers don't go there and ignite those fine fuels that have had the chance to get there beforehand. So I think in this country, in the United States at least, we talk about home survival or building survival in terms of managing things on the property and on the home. I call this a coupled approach. It can be called any number of things, but you take care of vegetation and other combustibles on the property and things on the home in terms of the construction materials and design features, how things are put together. This picture, the Northern California situation, you can imagine that if nothing is done to the vegetation, then a spot fire at least will be able to burn directly to the house. And if all the greenery were gone, most homeowners do not have the ability to manage enough vegetation or other types of fuels that they can preclude embers not reaching their house. So regardless of what happens to the to the vegetation and other combustibles on the property, the home has to be able to resist a wildland, has to be able to resist an ember or firebrand exposure. So that's why you need this coupled approach. You need to take care of the vegetation and combustibles so that radiant heat and direct flame contact doesn't occur to the home, and then do things to the home itself to minimize the chance of ember ignition of the home. And to the extent that your neighbor is nearby, then other material kind of decisions to minimize the chance of home-to-home ignition in those kind of scenarios. So whereas I'm going to talk mostly about the built environment, I'm going to spend a minute talking about what we refer to as defensible space. This is just how you manage vegetation and other combustibles on your property. And typically, it's you split your property into zones, and you start at the house and work out into just away from the house. Traditionally, it's been from the house 30 feet out and then 30 feet to 100 feet, let's say, or to the property line. I think the 100 feet came from the work of Jack Cohen back in the late 90s during the Northwest Territories Crown Fire studies, where his research indicated that 100 feet was good from a radiant heat exposure, and that's the rest sort of grew out of that kind of situation or situation. Yeah, let's leave it there. The newest part here, it's really not that new, but it's gaining traction, is this near the home zone, this 0 to 5 foot zone, or 0 to 1.5 meters, where you have approaching a non-combustible zone on the ground. So you don't have a lot of vegetation, if any, and you replace that with non-combustible options, whether they be rock mulch or other hardscape features such as a concrete sidewalk. And this is all because of the vulnerability of the home to embers. So you don't want things igniting close to the home that can result in flame contact or radiant heat to it, and sufficient to either break a window or ignite combustible siding, for example. So this is a newer thing. It's state law in California that will become official in 2023. And it's been actually a part of guidance for educational and outreach groups since about 1991 or 2. And it's gained traction since then, but it's taken that long to really take hold in a major way. So here's just some examples. These the left-hand pictures, the left-hand picture and the center picture are from the Waldo Canyon area, Colorado Springs, after the Waldo Canyon fire, 2012. And it just shows a good example of this non-combustible zone next to the home. And this zone has to include under the footprint of any attached deck. The lower right-hand picture, is a storage of a lot of lumber. You really can't have your own personal lumber yard under your deck and expect it expect the deck to do well, because embers will ignite that lumber or those boards if the home is threatened from wildfire. Prior to embers going there, you will have had debris accumulate in amongst those crevices there, making it far easier for embers to ignite that material. So you need to have a clean underdeck and a clean near home zone area. This is from the Marshall Fire in 2022, end of the year, December, in north of Denver, Colorado. And just an example of what vegetation in the near home zone can do. And so we have on the right-hand picture ignition of shrubbery, small plants that impinged on the crawl space vent. There you can see in the upper red arrow area. That also ignited this small tree, which became the big problem for this particular home, because it allowed a fire to burn through this combustible soffit into the attic and spread in the attic space and then into the home itself. So this home was badly damaged. It's a stucco cladding, so the wall is still standing, but the inside is pretty well gutted. So this is another example of the importance of this near the building zone, this non-combustible zone, zone 0. The 5-foot zone, or 1.5 meter zone, was just somewhat of an arbitrary number when it was first developed. It was best judgment based on the people in the room that day. In the late, in 2017 and 18, individuals at IBHS conducted an experiment just to determine under typical vegetation, using vegetation that might be commonly used, found near a home, is 5 feet enough? Should it be further? Is it too far? I mean, does it need to be as far as 5 feet? Can it be a shorter distance? And that was sort of the objective of the experiment. During this experiment, we used either wooden cribs or gas burner to replicate these kind of intermediate vegetation that might be in that neck of the woods in the area around the home. And as it turns out that for most situations, 5 feet is fine. For a cornering wind, you see on that C area on the right-hand part of the diagram, you should be a little bit further away than 3 feet using these kind of exposures. And that's because the wind blows directly into the home. The left-hand pictures show what flames do and various kinds of wind speeds, but the left-hand column, the A and C pictures are higher wind speeds, and you notice that the wind is the flame angle is away from the building. The building represented by the white rectangle, vertical rectangle, and then the B and D would be lower wind speeds where the wind can actually blow into the building itself. With the cornering wind, it looks more like the B, even at higher wind speeds. It just the flame angle and flame length is approaching the building, and that's why 3 feet is inadequate in that situation. So as a guidance kind of a thing, you want to minimize vegetation in the corner of in an exterior corner of the building. So part and parcel with the horizontal non-combustible zone or low combustible zone, or that in California this is going to be called the ember resistant zone. You need to have a vertical zone of comparable, well, not comparable, you need to have a zone so that embers that ignite, that land at the ground to land and accumulate the ground to siding intersection don't have anything to ignite. So you need to have this vertical zone that accompanies the horizontal zone. And that's what is depicted in this particular picture. We did some studies of this zone in the at IBHS in Richburg a number of years ago, and determined that 6 inches is a conservative number. You don't really have to worry about ignition from embers alone when you're at that clearance. The only time really where ignition occurred was when the siding came all the way to the ground. And that's the middle picture there. And the inset picture is the backside of that 0-inch clearance short wall. So I think that the 6 inches and even 2 inches is perfectly good from an ember ignition scenario only. I think the thing that's difficult to know is whether you have debris accumulation at the base of the wall or any kind of ground cover that might result in flame heights that would pose a problem to 2-inch or even 6 inches. So I think this vertical zone needs to be decided on based on what happens to be there. If you have a strictly non-combustible zone, and you can have some guarantee that debris won't accumulate. It's a hard thing to guarantee, I think, but the 6 inches is a good number, and definitely a conservative number from that perspective. So this is just a note about non-combustible cladding systems. Even if you have non-combustible cladding, construction often results in combustible components of the wall overhanging the foundation. And we see that in this particular situation, in this particular home. You can, if the right-hand picture, you can see some wood-based sheathing product that overhangs the stem wall of this particular home. This is taken at a different location on the same home. And I think it just indicates that even if you have a combustible siding or combustible cladding, you still have to maintain a non-combustible zone horizontally, or a low combustibility zone horizontally, and some vertical clearance so that embers can't ignite components in the wall in the assembly. So most of what I'm going to be talking about today in terms of mitigation strategies are what I would call active strategies. So these are things you do once, and with the exception of some routine maintenance kind of issues, you walk away. We'll talk a little bit about some, excuse me, I'm going to talk mostly about passive strategies. Active strategies are things that have a short-term benefit that you apply in advance of the fire arriving. So like a gel, or turning on an exterior sprinkler system, or putting a cover on a vent or a cover on a window. We're going to talk a little bit about these, but not focus on them. And so we're going to talk about exposures and strategies by component. And we'll start off with the roof. This is the way that often building codes address the vulnerability of a home, is by a component. And so we're going to take that same tact here. You'll see on this roof that there's one red circle and a number of yellow squares. The red circle is what you can be informed about regarding a standard test method. So the standard test method tells you about the performance of the roof away from intersections with other things. The yellow squares, I would argue, are as important or more important in that they point to other vulnerabilities of the roof itself. So where the roof meets a wall, where the roof meets a gutter, where the roof meets a skylight, like that, roof meets a vent. These can be equally or more vulnerable, especially from an ember exposure. So I'm going to talk about some of those things. This is, in the United States, we use a standard test, ASTM E108, to evaluate the performance of a roof covering. A comparable standard is the UL 790, Underwriters Lab 790. And this what we're seeing here is the burning brand part of that test. It's a several part test. You need to pass all parts to be have this particular class rating, fire rating. But we're just looking at the brand test at this point, and it's a fire penetration test. So on the right-hand picture, fire burned into what would be the attic space, and so as built, this particular wall roof assembly doesn't have the highest fire rating, which would be in this case of Class A fire rating. So it's Class B or Class C or unrated, but it's not Class A the way that it's built in this case, because you have the flames coming through the roof assembly into what would be the attic space. There are fire ratings are based on standard construction, and sometimes you need additional materials to meet the fire penetration part of the test. And this is an example of a roof covering. This is a wood shake, fiber retardant treated wood shake that can meet the Class A fire rating, but only if it has some additional fire barrier or fire resistant material in the assembly. And we're looking at a gypsum fiberglass product. The white panel is a gypsum fiberglass product that is incorporated into this assembly in order to allow the fire retardant treated shake to obtain this particular fire rating. Other kinds of materials that need additional fire resistant materials would be like a recycled plastic and rubber roof covering. They need an additional material other than the building paper and the roof sheathing that would be common in this country. And I should say that these roof tests, they really evaluate failure and not damage. So here we have burning pine needles that have been ignited by ember exposure on this asphalt composition shingle roof covering. This is a Class A fire rated roof covering, so the highest rating. So fire didn't penetrate through it into what would be the attic, or in this case, into the attic, but the roof covering itself is damaged. So you would be replacing that damaged part after this kind of an exposure. I think that's so it's just distinguishing between damage and failure in these standard test methods. So here's an example of where the vulnerable part of a Class A rated roof, this is again a asphalt composition shingle roof covering. It's Class A fire rating, but I would argue that the vulnerability of this roof is the wall next to it. It's a shingle roof with pine needles accumulated next to it. So you don't, this is again a situation where the protection offered by the Class A fire rating is maybe bypassed by the cladding adjacent to it. So at these roof to wall situations, you need to make sure that that doesn't happen. So you need to either replace the siding locally or do what we would see as add a flashing detail that I'll show you in the next slide. But I just wanted to point out the right-hand picture is just demonstrating that embers easily ignite this kind of pine needle debris. The right-hand picture is again from a test at the IBHS Research Center. There's an example we would use step flashing going up the wall to minimize the ember ignition potential if you have a combustible cladding. And again, it depends on how much pine needle debris accumulates, whether this 6 inches, let's say, is adequate to minimize ignition potential of the cladding. It might be, the strategy might be to replace the siding only in this area where the roof meets the wall, and with a non-combustible option to better protect that area. And if you do use a flashing detail, you want to make sure that it gets behind the cladding at some point, so that water can't get between the siding and the flashing, because then you would end up with a decay problem, which also you don't want to have. Just another example of edge of roof where roof meets other material. In this case, the edge of the roof, and you need to plug it. It's obviously on the right-hand side, and this is just a DIY homeowner doing the job, and I just took the picture before the homeowner finished it. So I'm pretty sure he's finished it by now. But this is using a mortar mix with a little red dye in it to match the tile, and you plug it so that birds and other debris can't get up in there. Bird nests and other debris can't get up in there, and it stops embers from going in there during the fire itself. I think it's important to know that you can have, even with this flat tile, where you don't have such the gap at the edge of the roof, you have it at the ridge. And so you need to make sure that you don't forget that gaps can occur at ridges also, and to plug those as they occur, or when they occur. And it's common in this country, at least, to specify a gutter cover device to minimize debris accumulation. What isn't necessarily in codes, it is in guidance, is to make sure that gutter cover device is non-combustible. In this case, on the right-hand picture, you see a debris accumulating on top of the gutter cover device, and it's a plastic gutter cover device. So it's not really buying you too much if the embers ignite the debris, which ignites the gutter cover itself, and then you have flames impinging on the edge of the roof, which are typically combustible, wood fascia, for example, and but the potential for fire to enter the house in that under eave area. So the left-hand picture is just demonstrating what embers can do at a gutter again. And then, a metal drip edge is a common feature for moisture. I think it's also a good feature for ember resistance and potentially for flame resistance should there be some debris in a gutter. And this metal flashing you see in the right-hand picture associated with the gutter. In this case, it's an integrated gutter that has this integrated drip edge that slips underneath the roof covering. This protects that edge where you have, on the left-hand pictures, you can see this, you have the roof sheathing coming down and then meeting a vertical fascia board. There's a gap in these areas between the sheathing and the fascia, and embers can enter and flames can do the same. The upper left-hand picture is without the metal flashing, the drip edge. And you see these dark things are the embers that entered into the soffitted eave construction in this case. And then the middle picture, center picture is the same kind of design, but with the gutter, with the drip edge. So no embers entered. It would also protect that particular edge should some debris accumulate in a gutter and it be ignited by the embers. Skylights are a common feature, and in this country you can have what's called a domed skylight. You see that in the center picture, and these are made of plastic and glass skylights, typically tempered glass, and you see that in the upper left-hand picture. Skylights can be vulnerable should flames touch them, flames ignite next to the skylight. And you'll see that there's a difference in accumulation potential depending on the slope of the roof. So slope of the roof also, I think, plays a role in the vulnerability of a skylight to a home. Skylights, the dome type, are less likely to accumulate. You see this in the middle, and but in this country, at least, it's deemed that the tempered glass skylight type of skylight is less vulnerable just because they're more resistant to flames. But it points to the need for the homeowner in this case to be a little more vigilant with regard to the debris removal from the roof. The right-hand picture is a steep slope roof and steep sloped roof. And this is a glass skylight, so a good choice here. But the steeper the slope, the more it acts like a wall, and so the more important it is for the homeowner in this case to be aware of what the vegetation is, straight out from that skylight, and to make sure that enough debris or vegetative removal and maintenance is done so that should that ignite, it won't impinge on or provide a radiant heat exposure long enough to do damage to that skylight. Okay, so we're going to talk a little bit about vents. These have been shown to be vulnerable to ember entry and ignition of things in the attic space or crawl space via post-fire assessments after wildfires. There's a number of kind of vents typically on homes that are vented. You have the foundation vents if you're built on a crawl space. We have a stem wall foundation as opposed to a slab on grade foundation. And then you have inlet vents in the undereave area, and then outlet air vents either at the through roof area or at the gable end, or sometimes both, but not necessarily both. So you have inlet and outlet vents. We did a pretty big study on the vulnerability of vents at IBHS. And one of the observations made was that regardless of what the vent is nominally, whether it's nominally an inlet vent or an outlet vent under natural convection kind of situations, when wind is blowing at a vent, that particular exposure on the windward side, it's an inlet air vent. So embers are going to want to come in if they're able. And on the leeward side, it's an outlet vent, no matter if it's nominally nominally in a in an outlet vent scenario or not. And so, and we see this on these through roof vents, the upper center picture, it's the inlet vent because the wind's blowing in that direction. And then on the other side, opposite it on the leeward side of the sloped roof, it's outlet vent. And you can sort of see that by the paper that I use as a ribbon, just so to visually see what the air is doing. So what we found in this particular situation is in the under eave area is that the open eave construction, the kind of construction you see on the right-hand side, those vents that are perpendicular to the airflow are pretty vulnerable to ember entry. And vents in a soffitted eave that you see on the left-hand picture are far less vulnerable to ember entry. And we see a picture here showing that. So the left-hand picture here is a gable end vent. It's the embers, the streaky light things are embers entering through that opening, to the screened opening. It's perpendicular to the airflow. And then here on the right-hand side is an under eave vent in open eave construction. And again, these are also very much vulnerable to ember entry. We had a lot of wood in this particular attic and we didn't ignite anything. So I think, part of this is what people store in their attic, and that could be, the thing that is vulnerable, or construction debris that sort of is left in the attic, sawdust that dries. Attic spaces are typically hot and dry places. And so things that are left in there tend to get dry and hot, which making them pretty vulnerable to ignition by embers. Hang on. I want to turn down the volume here. Sorry. So here we have a camera pointed at the inlet of the gable end vent, just showing the difference in ember size and number as a function of mesh size. This is 1/4 inch mesh, and you can see a large number of embers that are entering. And then we just went to it's an 1/8 of an inch mesh. The number has diminished, and the size of them has diminished. So, and one mitigation strategy is just to reduce the size of the mesh, and that would tend to reduce the vulnerability. And this demonstrates that reducing mesh size does in fact reduce the size and the number of embers that enter. And then we have one more here coming, the 1/16 of an inch mesh. So these are tinier yet, and still sort of the same kind of a number as with the 1/8 of an inch mesh, but definitely dramatic decrease between 1/4 and 1/8, and then about the same with 1/16. Some research or some testing that we did in developing an ASTM standard to evaluate the vulnerability of vents to ember entry definitely demonstrated that embers passing through 1/4 inch mesh screen had enough energy to ignite fine fuels in particular. And also 1/8. I just want to change. There we go. So the other thing that that happens in under eave situations is with mesh, at least, is the ability for flames to enter. So if you have fire burning on the outside of the building, then in addition to embers, flames can easily enter, as is demonstrated here. The other important item is between this open eave and soffitted eave construction. In this country, open eave is very common because it's cheaper to build. But based on the ember entry potential and the vulnerability of open eave to flame, as we see on the upper left-hand picture, you have easier to ignite and more rapid lateral flame spread once ignition does occur, compared to this soffitted eave on the right. So the open eave on the left, Suffocative on the right. Between the reduction in vulnerability to flame and the reduction in vulnerability to ember, this Suffocative construction is definitely the way to go. And I think building codes are moving that way to acknowledge that reduction in vulnerability with these different kind of construction methods. If you don't have flame impinging up in that area, then this is a question that doesn't really matter anymore. And so things that you've done to minimize that from occurring, such as this ember-resistant zone near building zone, go a step in that direction in terms of being able to minimize that opportunity for happening. The thing about finer mesh screening is that they're more easily gunked up. And we see that with the 16th of mesh screen in the upper left and the 8th of inch mesh screen in the lower right. The paint is bridging over the mesh in the upper left-hand picture, and then you just have a lot of debris in the right-hand picture. So the moisture management function of vents are more difficult to do when they can't function that way. They can't let air in this case. So it does definitely put another maintenance item on the residents' checklist to do in order to not encounter moisture-related problems down the road because of this blocking of the mesh vents. This is a ridge vent example. What we observed was that features that were good for wind and rain resistance were also good for ember resistance. So this upper left picture is a ridge vent with an external baffle, and that tends to do a good job of minimizing ember entry through the ridge vent. The lower right-hand picture is a ridge vent without the external baffle, and it points to the problem using plastic vents in this kind of situation, in a through roof situation. And that is debris accumulating at the entrance, and then ember, and what we don't see here, but is the ember ignition of that debris during a wildland fire when embers impinge or land on the roof. And then you have flame impingement exposure to the plastic vent itself, and ember and flame entry into the attic space. I think we're going to, in California, you can't use a combustible vent on the roof, and this is the reason why, I think. Although there are many ridge vents that are combustible or plastic, so that will be changing, I think, in wildfire-prone areas. There's one section in the California Building Code, Chapter 7A in the California Building Code that specifies what vents have to do, and the language says that vents have to be able to resist the entry of embers and flames. And that led to the development of a number of commercially available products that were intended to do exactly that. And we see on this slide just examples. Actually, these are all that are commercially available today. And the upper left, all of these vents have different design features, some that are for ember resistance, some that are for flame. For example, the upper left has a honeycomb mesh that's intumescent coating, and then a fine mesh screen on the backside for the flame and ember resistance. The lower right has a steel wool kind of matrix, and then some baffling on the front that addresses ember and flame resistance. The middle one uses a baffle design and intumescent tape to obtain the ember and flame resistance, and also a screen on the back of that. And then the right-hand picture uses, again, fine mesh and I think a steel wool kind of a product inside. The design of the far right one has changed, so it doesn't look exactly like this anymore. But these are in California at least, these are the vents that are commercially available that have been approved as flame and ember resistant by the state fire marshal's office. And again, I think, well, not again, but I think the other option is to go to an unvented attic and crawl space. And these are easier said than done with new construction, more challenging with existing. I think we'll see that many things are more challenging with existing construction, but this is an option, and then you don't need to worry about vents at all. So a little bit on exterior cladding. So we saw the right-hand picture, big box store in Santa Rosa, California, Tubbs fire earlier. This is the left-hand picture is from a 2003 fire in Southern California, the Cedar Fire. The siding is important, but not necessarily. There can be other vulnerabilities. We see these non-combustible walls and destroyed buildings. So there often are other things that are more important. Not that siding isn't important, but it's sometimes not the most important thing. So here's just the code in California. It's a fire penetration test for combustible cladding to comply. So the left-hand picture, if what happened on the right-hand picture didn't happen, then this cladding would be fine because the fire did not penetrate through the siding or through the cladding into the stud cavity. But we see in this case on the right-hand picture that it did penetrate. And so as built, this isn't an acceptable cladding, but these do point to the vulnerabilities of exterior cladding in wildland fire areas. So fire spread up the wall, impinging on other things along the way, or fire penetrating through the siding or cladding into the stud cavity and then into the home itself. We have done some mitigation strategies for combustible cladding. I think people talk about coatings, particularly intumescent type coatings, and then as a active strategy, applying a gel coating. And the other obvious thing is just to have this ember resistant zone horizontally and the vertical non-combustible zone, plus really good defensible space that minimizes the chance of that combustible cladding igniting in the first place. But other strategies that have been discussed would be this intumescent coating. IBHS did some research in collaboration with UNC Charlotte, University of North Carolina, Charlotte. And NIST has also done a similar kind of study. And both results indicated that the effective service life wasn't really long enough. So within a year, these coatings were pretty well performing about the same as the wood substrate. So not really adding anything to the performance. The NIST study used accelerated weathering. The IBHS UNC Charlotte study used a natural weathering. So we're seeing in this lower picture the natural weathering fence at the IBHS facility. We used relatively small samples. So in both the NIST and the IBHS cases, the results, the performance was based on performance in a cone calorimeter test. The IBHS UNC Charlotte results can be found in the fire materials publication shown here on the screen. There's some additional research going on. This one is a collaborative effort between IBHS and the United States Department of Agriculture, Forest Products Laboratory in Madison, Wisconsin. And in that case, we're looking at or evaluating a different kind of application method. And the results of that study should be available in 2023. Again, another collaborative effort between IBHS and University of North Carolina at Charlotte evaluated the performance of gel coatings. This would be an active strategy. You would apply it, as you are evacuating, and so our interest in is how long does that coating last, our basic finding was that within 3 hours or so, the coating was no longer effective. so I think in that case, our walkaway was that for a homeowner, not necessarily a good thing. For a first responder, probably perfectly fine, because the first responder might be able to come back and rehydrate after a while, the coating. But a homeowner, at least should be gone and evacuated. So good for first responder, not such a good idea for the homeowner and or resident. I think there are just other strategies that the passive strategies that would be better suited, I think, for a homeowner to reduce the vulnerability of the home. So windows, a lot of testing on windows, both in this country and in elsewhere. Australia, for example, has done quite a lot on the performance of windows. Two things that can be vulnerable: the frame or the glass. The research that I've seen indicate that glass is the more vulnerable component. And the glass, is vulnerable because of this temperature difference that occurs between the part of the glass that's protected by the frame and the glass that's exposed to radiant energy or flames. Should there be a flame contact exposure? Cracking from the edge propagates inward. If you have enough cracks, then the glass fails and falls out. Some back in the 1990s, research by Fred Maurer, who at the time was at the University of Maryland. He did a study at NIST and found that one exception to this, be indifferent to frame and glass being the most important thing, was the vinyl frame, where at radiant heat exposure is far less than that required to break the glass. You would have deformation, particularly in a hung window like this, as shown in here, the double hung. Well, I think this is a single hung window, but in a hung window with that horizontal interlock or meeting rail, that deformed IGU unit would fall out and break when it hit the ground. Subsequent studies elsewhere has shown that if you have a metal reinforcement in that interlock area, as is shown in the right-hand picture, that deformation doesn't occur, and the IGU unit stays in place, or the glass unit stays in place, and the you can become indifferent again to frame type because glass becomes the more important item again in this window assembly. And most vinyl windows have this reinforcement because of other code requirements for wind and sort of breaking and entering kind of things to make the locking mechanism hold well enough. So it's as long as this vinyl window has this metal reinforcement, then it becomes back to glass being the important thing. Like this is another example of damage versus failure. Vinyl is more vulnerable to radiant heat, and so you could have deformation of some component on the window that we see in these pictures from various wildfires. But again, failure didn't occur. And so it's replacing window versus, in this case, home. Window screens are often used to keep insects out. They do a good job of absorbing radiant energy, heat, and protecting the glass until the screen fails. This is a plastic clad fiberglass screen. It has done a job of keeping embers out. We intentionally left the window open in this case, and embers didn't come in until fire touched the screen, and then it failed. So, from this perspective, metal screens would be a better option. Some research that has been done indicates that any kind of screen can minimize the radiant heat exposure to the glass behind it, as long as it's present. And let's take a minute to talk about this. We've talked about these things on the wall individually, but I think we need to think about how these interact and work as a system. And this is a demonstration again done at IBHS in 2019. The right-hand picture just to show you what the ember exposure could be like. And this is the result. So this particular side of the building had combustible mulch, embers ignited combustible mulch. That flame ignited siding, which was a shingle siding, and you had sort of rapid vertical and lateral flame spread to the gable and vent, to the under eave, and over to the window. You don't see that in this particular picture, but it did get there. And failure was flame entry through the gable and vent, glass breakage in the window, and fire entry through the under eave on the rake end of the gable end of the building here. These things happened before fire penetrated through the siding into what would be the stud cavity. So these things, if the system needs to work together, you have to, if you have combustible cladding that is likely to have flame and vertical and lateral flame spread, then the things that it's going to touch have to provide similar protection, or in this case, more protection, so that the other things don't become weak links in of themselves. Embers and flame for decks. This is decks that are attached to buildings become a problem if they ignite because there are vulnerable things next to them, like siding potentially, or access doors or windows that we see all on this particular deck system. So embers landing on the top, flames coming from below. These are all things that these decks need to resist. If you have a non-combustible zone under the deck and away from the deck, then the deck just needs to resist ember exposure. And so these are two pictures. The left-hand picture from some studies at IBHS on the vulnerability of decks to ember ignition. You can see in the red circle that there are several ignition points on the deck itself there. And then the right-hand picture is the under-deck flame impingement exposure reference, a standard test method referenced by Chapter 7A, the California Building Code. And it is the way that decks comply to be used in the state of California these days in wildfire-prone areas. But notice in the left-hand picture that the deck is located several feet from the exterior wall of the test building. That is because these embers flow back and accumulate in an area away from the building. So we wanted to get the spot where accumulation was maximum, and that was sort of where this deck was located. So this picture is again demonstrating what we saw in the last picture. So embers accumulate at the deck, at the wall to ground. So whether it be ground or deck, it's sort of the same situation. And that's where the yellow arrow is pointing. And then some distance away, which is where the red arrow is pointing. And this is only applies to when you have a smooth surface. If you have a rough surface like bark mulch or whatever on the ground, the embers won't have a chance to flow back. They'll stop pretty much where they land, whether that be a cascading down the wall at the wall to horizontal surface area, or if they don't have enough energy to get to the wall, wherever they happen to land, approaching the wall. If they get to the wall, then they're going to accumulate at the deck of the wall we see in the upper right-hand picture, the yellow arrow, or on the deck itself, they'll accumulate in the gap between deck boards. And if they land at a place where there isn't a joist, they'll fall through and land on the ground. And if they land on a place where there is a joist, they'll accumulate there. And this location, the red arrow location, is where the embers will ignite the deck if it's going to happen. There is an above deck brand test that is tied to the California Building Code. It isn't used particularly because it's not required by the building code. It's just, it is a way to comply, but there's another way to comply that doesn't require this brand test. And this, as you can see, uses an E108 type of facility that is used to evaluate roof coverings. and it used a large 12-inch by 12-inch Class A brand as specified in ASTM E108. This it's probably just as well that this isn't used so much because it doesn't really represent the way that embers threaten a deck. They land, as you noticed, they land and accumulate in the gaps between deck boards, not sitting on top of it in any way. So this is a standard test method that is on the books, but not too well used. This is, again, some pictures from experiments at IBHS. And you'll notice on the left-hand picture, flame propagation after ignition of the deck boards above a joist and a deck board gap. It's a pretty tiny fire that propagates to the building. It takes a pretty long time. But typically a firefighter or a first responder won't be at the house. And so however long it takes is however long it takes. And whether it's a problem or not depends on what's at the house or the building when you get there, when it gets there. But it could take an hour and a half or so to propagate. It didn't seem to matter whether it was whether the deck boards were parallel or perpendicular to the house, to the test building. The propagation occurred just the same. Fires became big, as you see on the right-hand side, when the fire moved into that underdeck area. So the underdeck is more vulnerable to big fire, and the above deck, it takes more than one of these small burning ember ignitions on the top of the deck, and to burn underneath and heat up that between joist area before the fire gets large in the underdeck with that kind of scenario. Some mitigation strategies were to increase the gap between the deck board and to incorporate a foil-faced tape product, bitumen tape product. Basically, it took increased the space between deck boards, and it took the joist sort of out of the picture in terms of a combustible surface. And that didn't preclude the ignition occurring, but it made propagation much more difficult to the point where self-extinguishment occurred before it moved very far off of the joist. This points to a mitigation strategy should you have a wooden deck. What our results showed was that medium density softwoods were pretty vulnerable to ember ignition. Higher density materials such as plastic composites or tropical hardwoods, which had a fairly high density, were far less vulnerable. And so if you have a medium density softwood decking products, in this case, this was redwood that we're looking at here, but the same would be true for Western red cedar and other moderately dense products or comparable dense products. You could apply the flashing. In this case, it's just a metal cap, and you only really do this if you're redecking, if you're putting a new deck on. But what you can do, regardless, is remove the deck board closest to the deck, closest to the house, and put a metal grate or a metal deck board in the place. And that pretty much would provide, similar to the non-combustible zone, the horizontal non-combustible zone around the house. It would do the same thing for the deck. This is a little bit more challenging if the deck boards are perpendicular or an off angle. You need to do more structural support under the deck to put in this non-combustible member right next to the house. But given the size of the fire, the 1 or 2 inch flame height fires that moves to the home, if it met a non-combustible member 1 deck board or 2 deck boards away from the house, then that would result in damage to the deck, but not to the house. There's a lot of talk of deck enclosure. I would caution about deck enclosure if you can't adequately ventilate that area. Here we see water staining in the left-hand picture, water staining in this horizontally enclosed area with a deck board gap. There's no way for water to get out. So decay of wooden members and corrosion of fasteners would be the problem with this deck. If you're going to vertically enclose, it also needs to be able to ventilate. And so in this case, we're looking at, excuse me, a screen mesh enclosure that minimizes ember entry into the underdeck area and makes it harder for debris to get there. It's up to the resident to not put stuff under there. And just to remember, recall that if embers that land on the deck don't land on a joist, they fall below. We've seeded this underdeck area with pine needles, and did, during one experiment, did observe ignition of that pine needle strictly from debris, from embers coming through the deck board gaps. We blocked off, we screened off the area in front and in back, so the embers had to come from on top. The challenge to fencing is, or the vulnerability of fencing is that it ignites and in essence brings fire to the building. And we see that in this particular drawing, this photograph, sorry. I think there was a fire in a Dallas suburb just recently that really, again, pointed to the vulnerability of fencing as a pathway to the home. And so I'm going to spend a minute talking about this. It becomes a sort of a much bigger deal. In this case, these are brick homes. And so ignition was from fence to home or fence to shed to home. And it happened either, these fences that were running parallel to the homes, the fire would burn down the fence and then ignite the undereave area and get into the attic and then into the home. This happened on a number of homes. It was a small grass fire that burned to the fences in the backyards, and then that burned laterally to the fences that ran parallel to the homes, and then to the undereave area and into the homes themselves. I think this pointed to the potential problem with fencing. There's been a fairly large study at NIST recently completed that fairly exhaustive study on the vulnerability of fencing to ignition, both in terms of propagation of flame and also in terms of ember generation. They observed in their post-fire after the Waldo Canyon fire that fencing, wooden fencing, was a big ember generator. They followed that up just recently with some experiments, and that publication just came out a couple of months ago. Fencing, as we've seen this before, can be ignited just by embers alone. The more porous the fence is, the less likely it is to ignite by embers themselves. But if you have debris under the fence, as we see in this right-hand picture, then it is can be quite a bit more vulnerable. So the embers that ignite debris can then ignite, the ignited debris will ignite the fence, and then that can burn laterally to the home. Because during wind events, the burning fence might blow away from the home during higher winds, but the burning debris will burn to the home as a backing fire, if nothing else. So this fence issue is I think a vulnerability that is easier to address, but becomes more complicated with the parallel fence situation. So in California, at least, the guidance is, and actually in Firewise communities in general, the guidance is to put a non-combustible section of fencing where it attaches to your home. I think the question that some of the fire data and the recent NIST studies point to is really how close can that fence be if it's parallel to the home and still not be a problem. So I think that's ongoing research area. There is, so one last active strategy is the importance of, or the effectiveness of exterior sprinkler systems. I think they are becoming more commercially available. Exactly the best place to put them and how best to use them, I think, is still a little bit in question. In this right-hand picture, you notice that it was strictly a roof-mounted system, and they left the area near the home completely unwetted. And so if there are combustibles there, embers can get there and ignite them. So I think the guidance right now is a standalone water system, standalone power system, or a way to deliver. Those are pretty straightforward. There has been a really nice study, and shout out to Dr. Green there for his PhD thesis that lays out what we know and what we don't know about these exterior sprinkler systems. I think before we walk this way, we need to have sort of our eyes open in terms of what they will do and what they won't do. And given the fact that there are a number of commercial systems out there, I think more information to the public would be well suited about now. So I'm going to finish just by sort of summarizing what I've been talking about. And it sort of comes down to the fact that building codes, which many communities have these days or are thinking about having, really only address new construction. And I already live somewhere. I'm pretty sure all of you already live somewhere. And so the existing buildings are, I think, a challenge in terms of how to retrofit them and the best way to go about it. You can have the best building code in the world, but it's not really going to influence or impact those things that have already been built. So I did a sort of an informal study a little bit ago where I had different kinds of situations for a homeowner, for homeowners. So depending on how close your neighbor was, far away, close, whether you're on a slope, and those kind of situations. And then I had recently, at the time, I recently listened to a podcast that talked about how to spend your money on pitchers. There's a baseball podcast, and how to best spend your money. And so I thought, well, if we have a limited amount of money, how best would we spend our money to retrofit our home, given a given situation in terms of how close with your neighbor, close or far away, we're on a slope, those kind of things. And then I asked some colleagues, to spend that $25, given that that certain things cost a certain amount of money. And so these were relative numbers. And so here we have, replacing a roof would be $5. So I have a number of dollar values assigned to a number of mitigation strategies aimed at the roof, at the exterior wall, at attached decks, at vents, and at defensible space, combustibles on the property. What would you do? And how would you spend your money? And I heard back from some, and I think the thing that was surprising to me was that there was general agreement on some things, but not all things. And so where there was general agreement, we're on sort of the big ticket items, replace your roof. If you have a wood shake roof, that's pretty straightforward. Replace your siding given certain situations, do certain things to decks. But the detail-y things for strictly for ember resistance wasn't necessarily, always agreed on. And this just pointed out to me that even with people that think about this all the time, that they have different ideas of what the best approach is, which I suppose means more research would be useful that would help the residents know the best way to spend their money to get the best bang for their buck, given their situation. I think that's the thing. There isn't a generic fix for a given, for all homes. It really is going to depend on what you need to fix based on what your home or what the home or building might see. And then finally, sort of following on and trying to get at the guts of how to spend your mitigation dollar. An effort led by Alex Marangaitis at NIST recently published this NIST technical note that did a similar kind of thing in terms of identifying how where the home was situated on the property, what the housing density was, and the like, and to come up with strategies based on that. And this was all because of some federal and state money coming into California for home retrofits. And it was to come up with a systematic way to identify what should be done to a given home, given its situation. And this was the result. And some of the things that came about were what we saw earlier in the previous couple of slides. And I think there's a couple of really nice summary tables. Table A, which basically talks about ember or firebrand kind of exposures and mitigation strategies tied to them, and they're by component, so roof, cladding, vents, and then it's a rather long table. It's just not all here, but it's a good summary table, I think. And then the table D, so table A is embers, table D is radiant heat, and flame contact kind of exposures in terms of what to do there. And it provides some mitigation strategies for those. And the idea is that it would be, the strategy would be identified based on an assessment by a trained individual that would do the assessment of the house and property, and it's take into account slope, terrain, current vegetation, current combustibles on the property, current conditions on the home, proximity to neighbors and all that, and then come up with a strategy to reduce the vulnerability of the home. And then notice that we have some relative dollar signs for relative prices of the something, of the strategy itself. So I think everybody acknowledges, or I think it's acknowledged that existing homes is really something that needs to be addressed. In California and other Western states, I think we're seeing more money targeting retrofit, and this is a way to systematically identify best uses of that money. So really, in summary, remember the importance of embers, and whether you have a direct or indirect ignition scenario, remember how that's important, and then the detailing to make sure that you don't end up with a moisture problem. Material is important when we're talking about radiant heat, and then this coupled approach, I think it's really important to remember that you need to do both things so that you can address the flame contact and radiant heat part, and also the ember part. So I want to thank you so much for your attention, and thanks so much.